Okay, let's unpack this. Magnetometers. You've probably got them humming away invisibly in your pocket right now.
Absolutely. They're kind of the unsung heroes for sensing motion and direction.
Yeah, but there's this really groundbreaking shift happening. It's driven by something called tunnel magnetoresistance, or TMR. That's what we're digging into today.
Exactly.
Our mission is to pull out the key insights from our sources on, how these tiny sensors work, their evolution, and the surprising impact they're having.
Right. And it's important to remember, while magnetometers aren't new, they've been used for decades, automotive industry, standard in your smartphone.
Sure, standard stuff.
This TMR tech isn't just a small step. It offers really significantly improved capabilities. We're talking about opening up exciting new application areas.
Things that were, what, just inconceivable before?
Pretty much, yeah.
Yeah.
Things we couldn't really do effectively.
Okay, so maybe trace the history for us a bit. Where did this all start?
Well, the foundation is really the Hall sensor. It's been around forever.
Right.
Detects magnetic fields, measures things like position, temperature.
Yeah.
But it has its limits.
Mm.
Our sources point to things like low accuracy and a large offset.
A large offset, meaning like a constant error.
Exactly.
Yeah.
A baseline reading that's always a bit off.
Yeah.
And you had AMR sensors as an alternative,
AMR.
anisotropic magnetoresistance, but they had, well, limited applications. Their MR ratio, that's the change in resistance from a magnetic field, is typically less than 5%. Not great.
Okay.
The next big leap was GMR, giant magnetoresistance. That was actually a Nobel Prize discovery.
Wow, okay.
Yeah, it revolutionized hard disk drives. Its MR ratio was better, typically about 10%.
So GMR was a big jump, won a Nobel Prize. What makes TMR the real innovation then? Our sources seem pretty clear on that.
Yeah, they do.
They talk about it being more accurate, having less noise, and crucially, consuming less power.
Yeah.
What's the breakthrough?
It's fascinating, actually. It gets into quantum mechanics.
Oh.
No, it's cool. TMR works because electrons literally tunnel through a very thin, non-conductive layer.
Tunneling, like through a wall.
Sort of, through an insulator barrier between two magnetic layers. It's not classical physics, electrons flowing through metal. It's purely quantum.
Okay.
And that phenomena allows for an extremely large MR ratio. We're talking 100% or more.
100%. Compared to like 10 for GMR.
Exactly. And that massive change gives you very clear signals. Think like a definite yes, no, or a binary 10. Much less ambiguous than the older tech.
Right, so the signal is just much cleaner, much stronger.
Precisely. It makes things possible that were just too fuzzy or unreliable before.
Okay, so let's connect this back. What does this actually mean for, the devices we use? You mentioned hard drives.
Yeah, absolutely.
Yeah.
TMR basically drives all modern hard drives, and it's the foundation for MRAMs.
MRAMs, remind me.
Magnetoresistive RAM. They're non-volatile